Okay, cool. Let's start. Last time around, we're still sort of going through the introductory material. So one of the concepts I had introduced was that an issue with current systems is that they are not energy proportional, and essentially kind of this concept that our systems are designed for a much higher performance than what we end up using. So therefore, most of the times they are lying idle, and this is true for computing systems, but it's also true for a lot of physical systems as well. And as a consequence, what happens is that when they're underutilized, we actually end up operating them at a point where they are not very energy efficient. So this is a theme we are going to revisit later. We also talked about that just circuit technology alone, I mean, progressing as it has, doesn't kind of really end up helping things. Okay. So other so when it comes to energy proportionality, the strategy of saying that okay, we can make all components energy proportional and then we are going to combine them and the result would be energy proportional, that unfortunately doesn't work out because a lot of things we just don't know how to make energy proportional. So that really leads to kind of the second strategy, which is statistical multiplexing. That is, we think of our system as made up of many otherwise identical components, of many servers or things like that, and then overall we try to achieve energy proportionality by shutting things down whenever they are unused and playing games at the system level so that we hide things like that when we shut things down, when we wake them up, it usually takes time, so we cannot instantaneously bring them up. And then also there is cost associated with moving a function which we might be doing on one computer to another computer or one data center to another data center or occupants in one classroom to another classroom, for example. So anytime we have migration of tasks, it has cost associated with it. So techniques like virtualization and all begin to kind of help us. So we'll see again some of these later in the course. Okay. So another aspect which sort of people worry about increasingly quite a bit right now when it comes to energy is that they try to look at overall energy cost. So this is this notion that I can artificially optimize a system by shifting energy use from one phase of its life to another phase, and then I can claim huge gains. And so I can have something which is extremely energy efficient, but insanely energy hungry to fabricate. And that's, from a societal perspective, not a great trade-off. It may still have benefits because with energy, it does matter where energy is being spent. So if you are, I don't know, if you're in Saudi Arabia, oil is just gushing out. It has a different price structure and all than if you are sitting in, let's say, Japan, where there's hardly any oil, and same kind of thing. So when and where energy is consumed does have its importance, but the overall life cycle also ends up mattering because that essentially dictates what the overall footprint that we have. So this is some data out of Apple, and the interesting thing that you would see is this is for Apple's products overall. Product use, so this is electricity that we're using while running our laptops and computers and all, is roughly a third of the overall life cycle cost. Okay, and that's an interesting consideration. And in particular, you would notice that how manufacturing does come into play quite a bit in this thing. What do you think might affect these percentages? Like, there's clearly some assumption being made about to come up with these percentages. Any thoughts?
Product use is assumed how long you keep it.
How long you keep it, right? I mean, so I want all of you to answer. Anthony is the only one who answers. Okay, so product use clearly has an implied duration of usage there, right? And so if you are like me, swapping whatever, buying a laptop every time a new one comes out, I'm being grossly inefficient, right? I mean, and on the other hand, if you hang on to it, that's great. Okay, so So there's a whole bunch of other stuff that they kind of worry about, and I guess under push from various rating agencies and all, manufacturers have begun to take these things seriously. So, like for example, manufacturing using materials which are light, manufacturing techniques which are inherently more energy efficient, and things like that. Transportation, part of it is about how you package stuff and all. Okay, product use is the one in some senses what this course is concerned about, where the direct usage of electricity while you're operating the system, and then recycling, and then finally kind of the various facilities like when the product was designed and things like that. All those issues come into play. Now, while we are directly concerned about this, but you can imagine that all those other sectors, manufacturing, transportation, recycling facilities, are also indirectly made more energy efficient by the use of information technology. That's less of a concern for us in this class, but certainly plays a role. So information technology, yes, has itself has a footprint. Information technology also as a part of the solution to broader spectrum of energy problems. That's kind of another interesting thing. So again, these are hard to predict, but a lot of interest in recent years on looking at how information technology, by making things smarter, so to say, can begin to have a positive impact. And buildings, for example, are a great example where by doing things like occupancy sensing and shutting things down and all, there are clearly a lot of interesting features that become enabled, which normally were not possible. So I'll not go into detail, but there are a lot of projections people do in terms of how much can benefit. So there are teleworking is an example. So there are studies where people have looked at working from home. Is it a net positive or is it net negative from an energy perspective? What do you think? So something as simple as I'll telecommute from home. Energy positive, is it energy negative, or depends? If so, depends on what? Okay, so it depends on how far you live. Okay, what else? What car you drive, right? Or so that's one aspect. What about your home itself? Oftentimes, AC systems and at home are much more inefficient. Okay, I mean, I might be working home alone with my whole home being cooled or heated depending upon time of the year, and therefore its overhead costs are a lot higher than in a workspace like this, which is densely packed, and therefore systems generally tend to be more efficient and all. So on an average, you can begin to think in terms of there's probably going to be some distance where and some type of home and all where actually it may or may not be energy efficient. Okay, and looking at the city, for example, those who live on the valley side of the city, where there is more need for heating or cooling, tend to be more energy hungry. The residences there are more energy hungry, and for them to come to work is probably maybe more efficient because then the homes are shut off. So it's a even something as simple as that. Or people have looked into energy analysis of, let's say, watching movie on Netflix versus having it be delivered via DVD. Okay, so if you think of, let's say, watching movie on Netflix, where all is the energy footprint on that? It's not simply your laptop or TV or whatever. It's also the entire delivery infrastructure which exists, the network, servers, and things like that. And again, things are often ambiguous on these things. Just because we can virtualize a service or make it move into software may not always be a win under all conditions. Okay. And a whole bunch of other situations under which improve. Buildings have been a particular focus, as I mentioned, and part of the reason is that buildings are pretty energy hungry. Roughly 40% of total energy in this country, and similar thing for most Western societies, roughly 75% of electricity, third of the natural gas. If you include indirect natural gas usage, like that which goes into heating water and stuff like that elsewhere, and which you consume. So fair bit of energy improvement. So, and the other part which I mentioned last time was buildings are also very energy non-proportional. So what you see out here is this is again this is the computer science building at UC Berkeley. This is the computer science building at UC San Diego. One thing that you would note out here is that the total energy stuff, it fluctuates. So clearly there is a daily perturbation which is happening, which is indicating people coming to work and leaving. Okay, so like lighting goes up and all. But there's so much static load which basically keeps the building operating at a baseline thing. So this is essentially when the performance of the building is zero, at least insofar as serving occupants is concerned. It's in a pretty inefficient mode of operation. So buildings are very energy non-proportional. Shutting things down for longer duration is one part of the answer, which is you can basically, so like UCLA in recent years shuts down over winter, okay, and part of the motivation is that such a long drawn shutdown, they can literally shut down entire buildings. They shut off hot water, they shut off AC, things like that. Things which may not be possible if you're shutting things down for shorter duration, because by the time, like when you shut things down, it's time to kind of wake things up again, okay, for shorter duration buildings. So buildings are very non-proportional. So what has been happening is information technology is being used quite a bit to make buildings more energy efficient, and there are variety of ways it kind of ends up helping. One is you can begin to identify inefficient appliances. So a lot of times what happens is that appliances either get old and are not being replaced, and if you can identify, if the utility can identify, then could offer incentives and all, and kind of begin to provide some dollar incentives, for example. You can detect failures in the building infrastructure. So, for example, leaky insulation in a building, okay, which is leaving the HVAC running all the time, those kind of things. And then finally, you can use information technology to provide feedback or other things which can help users modify their behavior, conserve resources, things like that. So let's take each one of these as an example. When it comes to appliances, it turns out that whenever you buy an appliance, or just like when we buy a computer, you can have numbers about what its energy consumption is going to be, but its actual energy consumption in actual usage is often very different. So the data sheet number versus the actual in-use numbers tend to be quite different, and one of the things is by having the data on its usage and all, you can provide insight on how things are performing, as well as things which are extremely old. So now, for example, in some areas of this country, what has begun to happen is that using signatures in the electric current out of your household, they have begun to identify what kind of appliances you are using, in particular, perhaps how old, what make, what model the appliance is, and then they target an incentive towards you. Okay, so essentially, it's partly a privacy nightmare in the sense there's a lot more being known about your home, but from a utility perspective, they can begin to target these things. And same thing out here. So in basic thing is information technology in this context provides an ability to sense, incentivize, control. That's kind of a role which it is playing. So smart buildings are kind of a huge emerging, still emerging, but nevertheless sort of very active industry. Lot of work happening, both sort of from a information technology perspective, as well as from the industrial perspective. Okay, smart grid, that's the other place where information technology is playing a huge role. So if you look at so another physical system where these things are happening. So if you look at traditional electrical grid, it basically is kind of a one-way pipeline, essentially carrying energy from generation all the way down to end use. So one-way flow of energy. It depends upon what are called as dispatchable energy sources, and by that what we mean is that you have generators, and whenever you need them, you can turn them on. So that's how you kind of meet demand, and otherwise you kind of keep them off or on standby. And the loads are totally oblivious to what is happening on the generation side. What I mean by that is loads have no ability to say, okay, we do our work at a different time when energy is abundant, or so there's no sort of signal to the load to modify the behavior. All these three things are changing, and the critical thing out here is that, well, uh, electricity flow is becoming bidirectional, in the sense that homes are being equipped or buildings are being equipped with solar panels and such so that they can feed the energy back. But more importantly, overlaid on top of this is essentially information flow, which is bidirectional, which assists in these other dimensions. So non-dispatchable and intermittent sources, that's a biggie. So what's happening is that sort of wind farms or wind turbine farms, solar panel farms, as well as these buildings which have local generation capabilities, they essentially are being connected to the grid, and they become sources which are non-dispatchable. By that, what we mean is that we cannot just bring them up. If there is no wind, there is no wind. If there's no sun, it's a cloudy day, then tough luck. So they are non-dispatchable and they are intermittent. So this, for example, is how generation out of a wind farm looks like. It's not like a generator where there's a continuous clean power, but it's varying very significantly depending upon local climatic conditions and things like that. Solar is perhaps a little bit more predictable, but nevertheless, if it's a cloudy day, things like that, it will get affected. So non-dispatchable and intermittent sources become an issue. So how do you think information technology can help us with this? So I'm making the claim that by making the electrical grid smarter, by making use of computing technology, there's perhaps some solution at hand with these kind of problems. Okay, so we can share. So what kind of communication do you think we'll envision? Anyone here? Okay, I'm exercising my prerogative to modify the grading, which was enough. Okay, so it's going to be 20% class participation. Okay, now participate, guys. So silence gets 0. I mean, these are issues which I'm sure you read about, right? I mean, this is. So what ways do you think computational methods can help us out here? No, you got your 20%. No, not yet. But anyone else? How about you? You know, my undergrad students are a lot more active than the graduate students. It's very perturbing. I taught M16 last quarter and an amazing bunch of students. Okay, I mean, yeah. No idea.
Can you use I don't know, stochastic model to predict the intermittent behavior of sort of the wind?
Okay, good. So I could use machine learning type techniques and all to see whether there is some pattern. Okay, so that's a possibility. I mean, certainly there are weather reports. We kind of hear today is going to be windy and stuff like that. So there is some ability to kind of predict that could come into play. So that's a possibility. Okay, what else? I hope you are searching on Google for the answer to this. Hello? You're looking on Google for my answer to my question?
Yeah, I am.
Okay, so what's the answer? What was the question? Actually, could you shut your laptop, please? Okay, so.
Like for some resources like the solar, there is this optimal voltage or optimal.
Mm-hmm.
I don't remember when they're generating this power. in
Yeah.
response to the change of the environment.
Right. So I think the theme. So there are two very broad themes out here. Okay. One is we can predict, and therefore prepare in advance. Okay. And prediction doesn't have to be just about this. Prediction could also be about load. Okay. I mean, today is going to be a particularly hot day or stuff like that, or some event happening. So we can predict, and the other is we can help adapt. Right. So loads can change their behaviors if they had information. So how many of you have heard of things like demand response? This term you have. What does it mean? Yeah, you work in this area, right?
Yeah.
Something. Yeah. Okay. So what's demand response?
Their response is during peak hours, the demand of electricity is really high, and then the utilities has to do something to react to that, to respond to that demand. So when the peak hour comes in, utility has to either start a generator or things like that and then they're talking about either to change the demand response, change the demand to different hours so they can respond it differently. So it's basically between the user's demand versus their how they can quickly respond to their power factor, the convenience of power, or the usage amount they can deliver.
Okay. So demand response, to summarize what you said, kind of basically refers to the idea that there is a communication which is happening between the generators and the load. And one way to meet a shortage of electricity is to bring up more generation, but the other way of meeting shortage of electricity is to get loads to shut down. Okay, and therefore, so we can do a mix of both. So in demand response, what happens is that we send a signal to buildings, homes, saying there's a shortage and you need to reduce the load, and in return there is some pricing agreements and all that take place. And so big loads, so within the home, the meter talks to the appliances, and the appliance may shut down the AC, or loads which are shuttable, so to say, can be shut down or reduced to a more power efficient setting.
Does this actually happen in practice?
Yes. So the law in California is that anyone who is, I think it's 100 kilowatt hour load per month or more or something like that, essentially kind of excluding most homes and all, they have to be participating in this. Okay, so it used to be that these things were done manually. So in effect, someone from the so you would sign up for this, and someone from power company will say, now there's a load emergency, you need to shut down and you have to respond. Now there are very well established protocols. So essentially over a computer network, you kind of talk, and then how a building responds to it can vary in many different ways. It could range from just some static policy, we got this thing, whatever, some part of the building will be shut down, or lesser important thing, to more sophisticated things now, that where refrigerators and washing machines and all, they have little radios which basically listen for the signal, and then depending upon what state they are in, they can change. So like a refrigerator might just let the temperature drift up, for example. So those kind of things happen. Okay, so so information technology is playing a huge role, and kind of from a overall sort of grid perspective, what they're hoping is the following: that between a mix of this smartness coming from information technology, together with the storage ability, the ability to store large amount of electricity, we can somehow take care of these variations. So what you see out here is that what's happening is, like, during daytime, so there's a lot of solar power. During nighttime, the wind power goes up. And then natural gas and hydroelectric are being used to kind of follow the demand that may kind of exist. So there's a complicated matching of load and demand, and you are dealing with the fact that some of these type of generation capabilities are themselves intermittent, and sort of have to combine these things together to get renewable in place. So the term you will often hear is renewable integration. That is, the grid was never designed to have these intermittent type production facilities being in place, and then somehow by making use of information technology we can incorporate them. And the other part is that we can avoid having to make more hydroelectric and natural gas type things by shifting people's behaviors, by having them use the loads at different times, for example. So one of the reasons, for example, electric vehicles are viewed positively is that the charging might happen at night or can be done at night when traditionally the demand is low. So basically you are shifting, you're ending up with a better load profile. Doesn't necessarily work out that way. So what may happen is you reach home, you have plugged in the car, and now you are hitting the grid at the peak time. Evening hours is when people cook, watch TV, stuff like that. That's kind of the peak time usage. So things don't always work in an anticipated way. Okay, so what's happening then is that there is generation portfolio is moving towards these renewables. There's storage, so better batteries and all, and then or other ways of storing energy, and then finally demand response. These are kind of all the key thing. And if you ever if you have any friends in mechanical engineering, Professor Ray Gudd's lab, I mean they are doing some pretty cool stuff, and there are, so like in his lab he has this huge battery pack, which essentially the idea is that that battery pack together with a solar panel essentially provides a sustained thing. So on top of ACCLA and pretty soon on top of parking lot 9, going to be on top of ACCLA building, there's already a big solar panel. There's a nice website where you can actually monitor how much power it's currently supplying, minute by minute updates, actually more rapidly, and how much is being sort of used, what's the load profile and all. So being able to manage this charging, discharging, this when the load is kicking in, what's power available, all those kind of things, information technology is playing kind of a role. So insofar as demand response is concerned, is we want to make our loads more elastic. So we previously talked about energy proportionality. So energy proportionality was, I want to make it equally efficient all through. Elastic means that can the load change change the time of operation. Okay, so for example, instead of consuming energy at a particular time, can I shift it? So let's look at our computers. Do you think, is it an elastic load? Yeah, so to what extent are our computers elastic? Or how can we make them more elastic? Okay, so let's look at my laptop. I mean, certainly there's a high degree of inelasticity, right? I have to give a lecture, can't help it, right? I mean, that's what it is. But think in terms of, like, let's say your Amazon data center and all, okay? Could you make the loads more elastic? Are the loads elastic?
Like if you're going to apply updates or something like that, then that might take some computation power.
So updates could be moved on. What about other things? What are data centers used for? Let's say you're a Netflix, right? In fact, we have read all that how Netflix accounts for so much of the internet bandwidth and probably therefore also the energy usage and all. You could imagine that by appropriate pricing, maybe watching movies at certain times of the day is cheaper than the other. Okay, you could shift the load. You could, so there are ways in which you can influence. So not all workload needs to be done immediately. So backups and these kind of things can be scheduled at times of the day when there is less energy. And the other thing is by pricing, you could move behaviors as well. And you would see some of this if you ever subscribe to some of these computing services. You would see that the pricing in many cases depends upon which part of the country they are in. So that's reflecting relative cost of energy. It can also depend upon time of the day. So making loads elastic, making loads adaptive. Our homes and all, again, a lot of things are elastic and adaptive, right? I mean, when big loads like laundry or pool motor or these kind of things can certainly be shifted quite a bit. So energy proportional and elasticity. Okay, so the main thing that information technology is therefore doing in these grids now is to really help match supply and load. So it's better manage the supply and make the load elastic so that the overall system works much more efficiently. As part of it, so we already talked about the forecasting, we talked about load being shaped, load being made elastic. So prediction, load shaping, these kind of concepts come into play. Part of it is also depends upon our ability to move energy around. So it's not simply moving information around, but it's also moving energy around. So increasingly what used to be this one-way flow of electricity is now also becoming something, just like we route data packets, we also route energy. So that's how our grid is evolving. There are sensors all over the electrical grid, monitoring the grid, partly for just purposes like failure and all, but partly also to enable these kind of ideas. So at a very coarse level, then what we'll do in this class is that firstly we'll go into making low power, energy efficient computing systems. We'll talk about that at various scales. Mobile, we'll look into batteries because that supplies power to mobile systems. We are going to look at PC class stuff. We are going to look at networks and server type things. And then roughly a third towards the end, we are going to look at how information technology can make other complicated physical systems which have physical elements, but they also have computing playing a role. How can they be made more efficient? Okay, so moving on to that. So we'll start with kind of the very basic question, looking at information systems. Where does the energy go? And try to get some insight, because once we understand that, then we know what to manage, where to reduce, what is it that we need to make more efficient. So there's a bunch of references. So computing consumes energy. Okay. Now, in a very strict physics sense of the term, there you would, if you Google for about power and energy, as he was doing, hopefully, you would find. No, I was commenting on your Google habits in the lecture. Sorry to embarrass you, but pay attention. Come on, guys. So there is actually a field called reversible computing, which basically says that computing can be done at zero energy as long as you are willing to do it very, very slowly. Okay, as in infinitely slowly. So reversible computing, the term reversible comes from thermodynamics, which basically says when a process does whatever energy it takes from the surroundings, it gives back. So reversible computing and closely related term called adiabatic computing, this has been something that people from physics side, but a lot of electrical engineers have been very fond of. Our neighbors at both USC and Caltech, a lot of work there. They have looked at that, but they never kind of really panned out. Part of the thing is that there are other parts of computing which do take energy, such as clocks, such as storage, such as communication. So ignoring that sort of thing, if you look at computing, you'll find that the computing is done at very diverse range of efficiency. So things which are in microwatts or perhaps even lower to things which are much higher. So very crudely speaking, you have stationary type devices, you have mobile type devices, and what you would say is this emerging Internet of Things, implantable sensor type stuff, and they clearly range in kind of where they stand, kind of watts or hundreds of watts at the left end to microwatt type stuff out there. And similar analogy in nature also. So you have things at different scales which consume different types of energy. Now, despite a lot of progress that has happened in sort of artificial forms of computation, we still are quite far off. So that's the good news, that is there is a lot of headroom. And the comparison is always drawn with brain. So if you look at the brain is roughly 2% of the human body by mass. It consumes 20% of the power that we consume. So average consumption of human body, we are like a light bulb of 100 watt, okay, so roughly speaking. Power consumption of the brain is 20 watt. In that 20 watt, it does some pretty amazing things. A couple of years ago, when on the Jeopardy program, anyone knows what Jeopardy is? Yeah, the IBM computer? Okay. So IBM computer won. The only difference was that the human at beat was running on 20 watt. The IBM computer was running on many hundreds of kilowatts. Okay, I mean, so there are long ways to go. By the way, just interesting, I don't know, a CS PhD student called Michael Billow made the record Jeopardy earning on Tuesday. Just like someone from our CS department. Just a curious tidbit. He won. He won 57 point some $1,000 in a single game. Okay, pretty amazing. Okay, the guy was just on a roll. So anyway, those of you who don't know, Jeopardy is a quiz show which is very popular on the TV, or used to be very popular, still is. Okay, so going back out here, so brain does 10 to the power 16 operations per second. Brain has neuron and synapses. Those neurons fire, they are carried over synapses, which are the wires. So essentially, I have 10 to the power 15 synapses connecting the neurons. Each one of them carries roughly 10 impulses, 10 fires per second. So energy per op is 2 femtojoule per op, if you were to say that an op is an impulse, okay, which is debatable. By comparison, probably one of the, I shouldn't say recently announced now, but it's still recent, Cortex M0 Plus, which is usually considered to be the most power efficient processor that we currently have, consumes around 9 microamp per megahertz, which basically translates into 13.5 picojoules per op. Most of our computers are several factors worse. Okay, so this represents. So we are talking about pico here and femto here, and there is a factor of. So we are roughly 10 to the power 4 less efficient than brain in terms of computing. Okay, so lot of headroom to grow. Other ways of thinking about, so like for example, our supercomputers and all, they tend to be around nanojoules, so they're another 3 order of magnitude, kind of. But you are looking at flops, which are floating point operations. So a bunch of data like that. Okay. Just curious, how much do you think communication costs? More, less?
More, right?
More. Okay. More. How much more? How much do you think will it communicate for me to send a bit over a Wi-Fi network?
Milliwatts?
Okay, that will be the subject of next slide. Power versus energy. Milliwatt is power, energy. So roughly speaking, so it depends on how you communicate, obviously, but active forms of communication where you are generating the carrier and sending it out, they tend to be, let's say, another 3 order of magnitude worse or 2 order of magnitude worse than this. So computing is more efficient than communication, particularly if you are doing over longer distance. Communication does get worse as distance to the power something. So that brings me to the next point, power versus energy, which was kind of just the mistake that Anthony made. So power and energy are often used very loosely, often interchangeably, but they are different. One is energy, the other is rate of energy. Okay, so just in terms of units, power is in watts, energy is in joules. The area, if you were to look at a system, draw the power curve over time, then the area under the curve between 2 times is going to be the energy consumed. And same thing from the flip side, power being supplied by a generator or a battery is the rate at which it is supplying the energy. Okay, and then oftentimes to complicate stuff, when you see specs and all, they might simply give you things in terms of current, okay, and the voltage might be implied. So like, for example, in the slide out here, I had said ARM Cortex consumes 9 microamp per megahertz. What this is saying is that if I'm operating this processor at 1 megahertz, then it consumes 9 microamp of electric current. But that doesn't tell me anything about the power unless I also make some assumption about the voltage that we are working at, okay? And then to translate that into how much energy would it take to do some work, I also need to know how many instructions per clock cycle can be done, okay? So all these additional information need to be there. So when we talk about power and energy, one has to be a little bit careful that what is it that we are talking about. So they are used interchangeably. Which is a better measure, power or energy, depends on your situation. Clearly, in some applications where energy supply is limited, as in I have a battery or something like that, we do care about energy. On the other hand, if I'm plugged in, then I may care less about the energy, and power, thermal considerations and all might matter more. So depends on the type of application and all. In some cases power, in some cases energy, in some cases both. Power consumption can often be increased over a short period, so I can accelerate the rate at which I'm doing work and therefore burning energy, but minimize the energy overall. So let's take intuitively the following thing. So let's say I have to do some work in some time on a computer. So that's what we're talking about. I have two choices. I can run the computer at the maximum possible frequency and finish it quickly and then shut down. And the other is I can run it at a slow frequency and consume all the time, just finish in time. What do you think would be better? Firstly, which one has lower power on an, so in one case I have constant power. In the other case, my power is very high for some period of time and then it goes down to zero. Okay. Now, question I have is the following: that which one is better from a energy perspective? I needed to finish work by some time t. So when I talk about energy, it's essentially talking about average power. So which one has a lower average power? So let's say I have a workload, I need to finish in 10 seconds. Am I better off running as soon as possible and shutting down, or am I better off running slowly and taking all my time to finish? No, I did not say anything about how high I needed to go, right? So what is certainly true is that the number of clock cycles I would need have to remain the same, right? So for example, if I had 10 seconds and let's say 1 megahertz clock was sufficient for me to finish in 10 seconds, then that means that in 10 seconds I would have done 10 million clock cycles. I could run the same system at 10 megahertz for 1 second and remain idle for the remaining 9 seconds, and that will give me the same number of clock cycles. Okay, even this is debatable, but let's assume that clock cycle is a good indicator of my ability to finish the work. My question is, which one would be better in terms of energy or equivalently average power?
I think it depends on your idle state. If you can power off or go in sleep mode, then you can save a lot.
Okay, so partly the answer will depend upon what is happening when I'm doing nothing, the idle part. Okay, what else will it depend upon? Right. I mean, so I also didn't say anything about when I bump my clock speed from 1 megahertz to 10 megahertz, am I paying 10 times more in power? Am I paying 100 times more in power, right? I mean, it will depend upon that ratio. So there are two things which matter. What's the relationship between power and speed, right? So as I change speed, how does the power change? Does it change linearly? Does it change quadratically or more? And the other part is, while I'm doing nothing, what is that baseline power, right? Because that would play a role. So we'll see later in the slide set what happens. So what may end up happening also is therefore because of these issues, it may end up happening that a component may be better in one dimension like power, but may be worse in energy or vice versa. Okay, so that relationship can be pretty complicated, and also under different settings. So for different type of tasks, the relationship may differ also. Energy and computation complexity. So that's the other thing, which is, let's say we would say I'm designing an algorithm. I want it to be energy efficient. Is that the same as saying that it should be computationally efficient, fewer instructions? Is fewer instruction always a better measure of, a reasonable measure of energy? But before I go, so I also wanted to comment on, so I said that I sped up the clock to 10 megahertz, is it always, so if assume that at 1 megahertz the system would have finished my task in 10 seconds. Is it fair to say that I speed up the clock to 10 megahertz, CPU clock to 10 megahertz, it will finish in 1 second? Oh, yes? No? Why not?
Local operation will be like yesterday forwarding some network.
Okay, so there may be stuff on the network, but let's say I don't have, let's say my stuff is just, doesn't do any I/O, doesn't do any external world I/O.
The memory access.
Memory access, right? I mean, memory access may not scale the same way. So clock only affects the CPU speed. I still have these parts of the system which don't. So even that assertion doesn't hold true. So all those things one must question. Okay. So energy versus computation are two distinct. Well, what is certainly true is that as I increase the number of instructions, number of memory access, number of I/O access, number of clock cycles per instruction, all of these things, both energy consumption and computation time increase. But the correspondence is, most cases, not 1:1. For example, in many processors, changing the order of instructions can affect how much energy they take. There may also be power management features that the processors have which can affect things. So it can affect computation time and energy consumption differently. So you have to kind of, while it's a good proxy, so while it's reasonable to say that in most settings, it will probably be true that a big difference in number of instructions needed by one algorithm versus other will translate into sort of energy, but doesn't necessarily always hold.
So that I didn't know that how you can be better in power but worse in energy.
How can we be better in power and worse in energy?
How the equation will work at the end of the day, it's E equal VI.
So a component may be low. So I'll give you an example. There are many processors out there which are lower power, as in when you run them at their maximum speed, they consume much less power than a different processor. But if you look at in terms of energy they consume to do the same work, they are much worse off. So I'll take an 8-bit microcontroller. Very simple, will struggle to do an FFT. But it can do it, right? I mean, it's a computer after all. I can fake floating point and do everything and all. So it would be very efficient when you look in terms of power, but at doing my task, its energy consumption may actually be worse than, let's say, my 100-watt Intel processor. So that question. So there's an architectural, that lower power can come at some architectural features which cost you. Okay, so modern processors, for example, differ in pipelining, number of execution units may have. So they may have the same instruction set, but they may be architecturally very different. And that architectural difference translates into that the more complicated architecture will have a higher power. It has just more transistors. But when it comes to doing some work, it may, for particularly kind of large amount of work, the more complicated processor has the advantage.
Say one of them has sensitivity of time and the other doesn't have sensitivity of time. So
What do you mean by sensitivity of time?
as I'm looking from the perspective of math.
Mm-hmm.
At the end of the day, you have E equal VI.
Sure. E equal to?
dt, sorry.
Equal to integral P of t dt, right?
So at the end of the day, they are proportional. So
No. At the end of the day, there is also the limits on that integral.
yes,
0 through finish of computation.
dt, yes, dt.
No. So there is dt, but the integral has to be from start to whenever you finish, right? So it's not simply, it's not integral between the same limits. So if the processor which is higher power, because it has a more complicated architecture, can finish in fewer instructions. That's the part of the equation that we also have to consider. So what ends up happening is, so in my example of the microcontroller doing the 50 and the Intel processor doing the 50, the microcontroller will have to would have to emulate a lot of the stuff. It has 8-bit data, let's say, or 16-bit data. It will have to do more instructions and all. So whatever advantage it had on power disappeared because it has to do more instructions. Okay. So it can take baby steps to, it just has to do more instructions basically, right? So it will end up taking more time. So, okay. So when it comes to then comparing or having energy as an objective, the first problem that we often end up facing is, what are we trying to optimize? Is it power? Is it energy? Is it something else? Things may be, I may give you a lower power system, but if it is slower, then you are worse off. What is it that you should optimize? So even the metric can be often difficult. So there are all sort of stuff which are used. Sometimes people talk about performance per watt. So this is basically saying that how many MIPS can the processor do, instructions per second per watt. Energy per instruction, that's another possible metric. Power delay product. Now power delay product is the same thing as what? Energy. Power delay product is the thing, energy. Energy delay product. So energy delay product is kind of interesting. It is trying to assimilate both how much energy you take and how much time you take. So it's trying to balance speed and power both into the same metric. These kind of single objective type functions, they are nice, but they do not explicitly tell me anything about what's the desired level of performance. For example, it's possible that a maximum performance per watt may be achieved by doing a setting so that my performance is 20% worse than without any power management. So let me put it another way. So let's say I were to we are in some sort of a benchmarking game, which system is better, and we decided we are going to go with performance per watt. And you could certainly set your system to operate at the best performance per watt, but then it may not be. It may be at such a slow speed that it may not be sufficient for us. Okay, so the setting at which I achieve one of these metrics may not meet my performance requirements. So what that leads to is more direct metrics. So for example, kind of the idea out here is that you basically begin to look at both aspects explicitly, performance and energy. So the clearest metric is, if I have a time requirement, that is, my work has to finish in 10 seconds, then I would say I want to minimize energy subject to that. Or I may have a different way of looking at it, which is, I want to make my battery last, or whatever, not want to consume more than a certain amount of joules, and I want to say maximize the work during that. So I have $1 worth of energy that I can afford, maximize the work done. And the flip side is, I have to process this image, minimize the power, minimize the energy consumed. Okay, for that. I need to process this image in 10 seconds, now do it. So the time constraint. So in the first version of the problem where I said, process this image, I left unsaid how much time. So you could conceivably come back and say, I'm going to take infinite time, and it would be very low energy, but that may not be sufficient. So there's always an implied acceptable time period. So metrics, what metric you're optimizing has to be done carefully, and in general, as with any optimization problem, there are going to be constraints, and there's going to be some objective that you have to meet. So it could be minimize cost subject to performance, or maximize performance subject to some cost in terms of energy. Okay, so let's see. When it comes, so we've seen this thing, today's computers are still very far from energy proportionality. The key thing so what ends up happening, again, to kind of repeat something we said, that most of the time they're operating at a low utilization mode where they're particularly kind of inefficient. So what we would like to have is that somehow, given sort of computers which are energy non-proportional, what you would like to have is something which behaves like this, which is its efficiency is always 100%. And what that would mean is, that somehow it will make sure that its power changes linearly with the utilization that we are getting out of it. So if it is fully loaded, it should be consume the highest power and then kind of linearly kind of degrade. Reality though is that right now hardware is not like this, and therefore one needs to power manage them, which basically means one needs to figure out ways of shutting them, slowing them down, all those kind of things to be done. Very broadly, as we'll see later in the class, there are two strategies that, as the example that we had earlier, one is I can slow things down, and the other is I can shut things down. One is called scaling, that is, as the demand changes, I scale it, and the other is when I'm not using something, I shut it down. So those will be the strategies that we'll be seeing. So let's look at where are the inefficiencies. So one problem that our systems face is that they are left on even when the service is not needed. So our PCs are left on even when we are not using them, our other devices. So studies have shown, these are numbers that are a few years old, but by and large they remain true. A lot of PCs remain up even after work hours. Sleep mode is not used that often. This number has probably increased, but nonetheless not a whole lot. Part of the reason, one of the reasons is oftentimes, particularly in older operating systems, sleep mode was very unreliable. That is, it will go on sleep and not come out of it, so therefore will not put it to sleep. But there is another reason for it, which is oftentimes we are using these devices as servers. So our home PC and all still needs to remain up because maybe we'll have an incoming call on Skype or something like that. Okay, so we are using these systems in an always-on mode because some of the applications we are doing are of that nature. Similar data for home PCs and stuff like that. This is out of UC San Diego. Okay, so essentially in the UC San Diego CSE building, they have 100 kilowatt of flat line, which is no one is in the building, and then just the PCs out there are consuming that much power. So tremendous amount of wastage because of variety of these factors. Just curious, how many of you use sleep mode in if you have a desktop PC? Sleep mode on your desktop PC. Huh? You don't use desktop. Well, those of you who are in research groups, you do use desktops. Ah, great question. Okay, so obviously you don't use it, right? What about your laptops? Okay.
I used to use sleep on my desktop, but then it's no longer wired into the network, it's wireless. So now I have to leave it on if I want to connect to it.
Exactly. So you fall into this category.
Yeah.
You want to be able to connect to it, and therefore you want to leave it on. Yeah. Okay. Then the other issue which comes up is even when we are using it, we use it very sporadically. Okay. Right now, look at my laptop's usage. Right. I mean, probably talking for a couple of minutes for each slide. So if you were to actually look at the usage within the computer, it's probably going to be that it's really doing useful computation very tiny fraction of the time. Most of the time it is just waiting for my next input to do something meaningful. Humongous amount of time. If you look at how much time deep down in the operating system, there's some piece of code where it's basically waiting for the next thing to be done, and there is this little idle loop. It's basically saying waiting for the next event. And this is some old trace I had collected, but on a Unix machine running X Windows system. But the interesting thing was that almost all the time, like 96%, 97%, was time spent in that idle loop. Okay, basically waiting for something else. The problem is that these times spent in the idle loop are often very tiny, so you cannot shut things down, bring them up very easily. Okay, there are ways you can begin to do it nowadays. With power having become important, but in the older days it was really very hard because when you would put things to sleep, it would take time to come back up. So these opportunities were effectively non-usable. Nowadays things have improved considerably. So that's the second problem. So again, to recap, first problem, they are left on even when the service is not needed. Sometimes we are unaware that these things exist. Sometimes for a variety of reasons we cannot make use of them. Second one is even when they are actively being used, there are these micro periods where we don't need them and we don't usually have an effective way of not doing that. In case of cars, for example, a good example is we often stop at stoplights. So those are like our micro stops. But most cars do not shut down, right? Some do. Some cars have, because European cars apparently are required in Europe to have this ability that they need to power down the engine when the car has stopped, as long as there is enough battery energy. And also some of the higher end European cars basically have this capability where at the stoplight the engine just shuts down. Okay, but most cars are not like that. Third problem, configured for peak performance, and this is something that we variant of that we saw earlier. Systems are notoriously over provisioned and underutilized. So what we do is we buy things which are an overkill because a tiny percentage of the time we need that capability, but most of the time we don't use it. So, but that comes at a cost because hardware which is optimized for a higher performance inevitably sacrifices its efficiency at the lower level. So it's kind of equivalent of saying if I buy a car with a 500 horsepower engine, it is going to be less efficient even when I'm drawing slowly. Okay, so I've raised everything in the baseline. Same thing is true with our computers also. So so we over provision, and then we actually most of the time, once in a blue moon, we might race our car. Most of the time, we are actually driving at 30 miles per hour, and that becomes a problem. So there is a huge non-linear penalty that we pay, and the same thing is true for the computers. Okay, so when we look specifically at computers, then very broadly, I mean, if you were to think of like where power goes and all, you can think the major subsystems that exist. So starting with kind of the core computing, so it's a processing part, and there are many different ways we do processing. So we could use processors as in CPUs, but there are DSPs, there are excuse me, there are ASICs, and then all of this is supported in memory. So there's processing. There is networking and I/O. That's a very critical component. There are peripherals, disk, display, GPUs behind it. Okay, that's another source. There is the physical world interfaces, so sensors and actuators and stuff like that. And then finally, there's a power supply, which may have a battery, charger circuitry, this DC to DC converter, which anyone knows what does it convert? Okay, partly it does that. What else does it do? Yeah, so it does that. What else? It also cleans it up because most our processors need very stable power supply, and also it regulates it. Okay, so that's the other thing. So it cleans up and it generates, like you said, different power, different voltage values. Okay, all of these are actually sources of power consumption. Okay, now it might seem kind of weird to you that power supply is a source of power consumption, but power supply have inefficiencies. They dissipate heat. So the batteries have inefficiency. Every time I put a charge into the battery and when I extract it, I get a little bit less because it leaks energy. So all of those things come into play. So peripherals, processing, communication, physical interfaces, and so let's start with the processor. That's kind of the simplest, most well-studied thing. Okay, so this is a relatively recent Intel processor, 22 nanometer technology. If you look at it, I mean, these things are now multiple cores. So in this case, there are four real physical cores. There's the graphics out here. There's a L3 level 3 cache. There is additional sort of system management stuff and all going on. Okay, so deep down though, everything is transistors. So a little bit of EE out here. Our digital circuits, our gates, fundamentally are made up. You can think of them as they are driving capacitors, and there are switches which are formed through transistors, which connect us to supply into the ground. So the so-called N transistors and P transistors, which form part of the gate. One source of power consumption, this going back to your high school physics, is that every time I charge or discharge this capacitor, so whenever this output is 1, this gap is charged up. Whenever this output is 0, this capacitor is discharged. So I have to supply current from the power supply, or I have to remove the charge through this transistor. These two transistors are like resistors. So what we have is resistance, capacitance, and therefore whenever we charge, when we put the charge out here, some additional energy we are going to be burning, dissipating as heat in this transistor. And when we remove the charge from this capacitor, then some energy will be dissipating as heat in this transistor. So the act of charging, discharging itself results in an inevitable loss of heat. If we magically had perfect switches, namely switches which had no resistance, then we would be good, because then whatever energy we would have supplied to cap, we would remove it in the discharge cycle. So whatever goes up, bit goes up, has to come down. The bit changes have to alternate. So in the perfect case, that's how things would have been. But because of these resistances, we are going to inevitably dissipate heat. So this is the so-called dynamic power consumption, which results from repeated charging, discharging. What factors do you think will affect this power consumption? Switching frequency. So how often we are switching, which in turn is dictated by the clock frequency. So it's basically saying that faster the clock, the more the dynamic power consumption, and in particular it's going to be linearly proportional to that, right? I mean, as I increase the frequency, then I'm just going to, if I'm doing the same computation, then same number of transitions are going to happen. Okay, so that's one. What else? Yeah.
Voltage.
Okay, voltage. Whatever is my swing in voltage out here is basically going to dictate that, right? So that's the swing that capacity. So voltage. What else? Capacitance, right? I mean, so just looking at this, C and V, those are going to be the two things which are going to affect things. So voltage and capacitance are, now capacitance we really have very little control over because that's decided at design time. Voltage we can have some control over depending upon whether boards support that. So indeed you can have software programmable voltage, and same thing with frequency, depending upon how things were done, you can have control over the frequency. So it's a mix of these things which can dictate, which can affect that. Okay, next one, another source of power consumption, which is the following. As we change from 0 to 1 or 1 to 0, we are turning one switch on and the other off, or vice versa. There's a tiny period of time where these guys are still in some halfway state. So it's not like we shut one off and then turn the other on. There's a period of time where kind of both are quasi conducting. So there would be some tiny amount of current. So if you look at the current profile, as these bits are flipping, there's going to be a spike. And that spike can occur every time there is a change happening. So this is another type of dynamic power consumption. And this too, like the previous one, will depend upon the frequency. That is, more often we do it, the more often we are going to see that spike, and the area under that spike is going to be the energy I'm wasting every clock tick. And this too is going to depend upon the voltage. Third one, so these two were dynamic. The third one is static. And what that refers to is that these transistors, the way they are designed, internally they have diodes, and they always leak a little bit of the current down to the base silicon. So this is called leakage current, and it's the fact that it happens because of a variety of underlying physics reasons, something called substantial leakage and something called tension leakage. Main point is this is static. And what that means is that this thing is happening as long as we are powered up. Even if I stop the clock, so I'm not doing any computation, this static leakage will still happen. So going back to the example I had earlier on, where it said I can do something in 10 seconds or I can do something in 1 second. In the 1 second case, if I were to power off the processor for the remaining 9 seconds, then I will not be spending the static power. So I have three possible strategies in that example. One is slow for 10 seconds. Other is fast for 1 second and then I stop the clock or run the clock very slowly for the remaining 9 seconds. And the third is fast for 1 second and shut off the processor for the remaining 9 seconds. So what's happening in case 1 is, in case 1, I will pay static for all the 10 seconds and I'll pay dynamic for all the 10 seconds, but my frequency is lower. Case 2, for 1 second I'm paying dynamic, but I'm paying static for all the 10 seconds. And case 3, I'm not even paying static for the remaining 10 seconds. So this static power consumption happens as long as the processor is powered up. So going back to my example, why would I not shut off? Are there reasons for me to not shut off the processor for the 9 seconds? So one is I can stop the clock. I can just not do the computation. And the other is I can keep the clock. I can not only just stop the clock, but actually power off the processor. Huh? Yeah, or alternatively, I need to do some action to save the data, right? I mean, because I have to restart, right? So if I'm going to be idle for a long time, then power off may be effective, but for small periods, I cannot power off. So data can be lost is one issue. Also, starting up needs a lot of, you have to, I mean, instead of just saying data is lost, the state is lost. So a lot of rebooting type actions have to be done. Also, power supplies and clocks and things like that take time to stabilize. So whenever I shut off the power, you bring it back up, your voltage needs some time to settle down. So all those issues kind of come into play. So to summarize this thing, then we have switching power consumption, which is charging and discharging of capacitors. That's dynamic. There is short circuit power thing, which also is dynamic. Both of these depend upon the clock frequency. And then I have this leakage stuff, which is happening as long as I'm powered up. Okay, so this is constantly there, and the only way to avoid this thing is to shut the system off, like power it off. This is a problem even when you are in standby. So the so-called sleep mode and standby modes and all, they don't really take this away. You still have this. It is proportional to chip area. As long as you have silicon, it's going to leak, and it also depends upon the temperature. So higher the temperature, more the leakage. Now, historically, like if you go back maybe a dozen years ago or something, this stuff used to dominate, the first one. Second stuff is tiny. This one was negligible. Now this has become the critical factor, and like as much as half could be the leakage. Yeah.
Why there is no leakage? Why you are discharging the upper one?
Say it again.
Why you only consider the lower transistor in the leakage? Yes.
Oh, in the leakage? Oh, it's in both. I just read it. It's everywhere. Any diode, any junction, so that means any transistor is going to be leakage. Okay. So there are other sources of static power consumption also. So oftentimes what happens is you might have chips which have analog circuits, with op amps and stuff like that. They always draw some current. There would be I/O pads. There might be things that you are driving, like a chip is surrounded by some stuff. So all of these things can also result in power consumption happening. So that's always there. So to pull it together into some semblance of a model that one can think of, so you can say that power consumption is equal to something which is switching related, something which is short circuit related, a term which is related to the leakage, and a term which is the rest of the static stuff. And then to further flesh it out, so the switching power one is proportional to capacitance, proportional to square of voltage. If you might recall your high school physics, the capacitor energy formulas, you would recall that there's a V squared term. So CV squared, F is the frequency. Alpha says that not on every clock tick am I charging or discharging. Okay, so the bit does not flip on every clock tick. So this is saying what fraction of the clock ticks am I actually active. So alpha CV squared. This guy again has the same alpha because it depends upon every time we are switching. Voltage is proportional to the quadratic frequency, and there is a short circuit current term. Leakage is leakage current times V, and this leakage current itself is complicated, depends upon temperature, voltage, whatnot, and then finally rest of the stuff. And from this you can compute the energy. So the energy is going to be power times the time duration. So if I'm looking at some time window delta t, then energy is P times delta t, and that F times delta t is the number of instructions that you will execute during that time period, assuming a processor does one instruction every clock tick. So this is my energy term. So now if delta t corresponded to how much time my program took to finish, then this is the number of instructions in the program. And likewise, the remaining terms will come into play. So this begins to be kind of a model which is applicable to essentially modern digital circuits. In an aggregate form, this is actually a pretty good description of arbitrarily complicated chips. Okay, so you can think of it as a parametric model, and then we are trying to learn parameters corresponding to this for the entire chip. So for an entire chip, C would correspond to some sort of a effective capacitance for my entire chip. We are not worried about capacitors for each place in the circuit, but like my overall processor corresponds to something like this. So this is the model bottom. Now looking at this, to lower power consumption, let's say for the moment switching power consumption, C I don't have any control over, but voltage and frequency I potentially could. Now one thing it indicates is the following. Let's say I give you a system where you cannot control the voltage. Voltage is fixed, but you can control the frequency. Looking at this, is lowering the frequency a good idea? Or if I lower the frequency, what does it help me with? What does it hurt me? No. So voltage is fixed in many computers. I don't have control over voltage. I only can change the frequency. So my question is, looking at this, can you say intuitively, looking at this, can you say that what would lowering the frequency help with? Right. So power would be lowered, but energy will go up. Okay. The reason is the leakage part, right? So lowering the frequency will let me run the system cooler, okay? Because power is going down, and there might be secondary effects as a result of that, because my cooling system will have to work less hard. But since I'm going to take a longer time, I would therefore burn static power over a longer time duration, and that would hurt me. Okay, so just slowing things down in the presence of static stuff, leakage and static power, is a bad strategy.
I think it's not only the leakage, as the E has a sensitivity of time, so it appears in the N also.
No, not really. N is the program, right? So think of it this way. I have a program which takes N instructions to execute. It will take some amount of time. So I would measure how much energy that running that program took, right? So I have an N, which is how much for that input, how much that program took. So this term is going to be whatever it is. Okay. So this term, time term, disappeared because this is what we have now. So from an energy perspective, as I lowered the frequency, this guy is unaffected, right? I mean, because I didn't have any control over the voltage, so that's what it is. Nothing has changed out here. So this term is fixed. This term is fixed. This term went up because delta. Let's see. This term will go up because delta t will go up. Delta t would be higher because I'm running at a slower frequency, so I'm going to take more time, and this term will go up. So lowering the processor speed helps me with power, and therefore will run the system cooler, but it will not help with the energy. We will actually end up consuming more energy. Okay, now there are second order effects that can kick in. So the second order effect is because my system is running cooler when I lower the frequency, therefore the effect would be some of my leakage terms and all would be lower, and therefore those effects might help me, but usually not to the extent that they will compensate. So I leak will go down because I'm running cooler, but delta T will probably go up more. Okay, so it's going to be a tricky balance out there, but ignoring those second order effects, running slower is not a good strategy. So what would be a good strategy? How can I, so if I'm lowering the frequency, I should also do something else, and that's what sort of was the comment there, which is lower the voltage as well. Because if you lower the voltage as well, then I could benefit on the energy side here as well. Okay, so what would be the problem with that? So firstly, can I lower the voltage? If I'm running slower, I can always lower the voltage because lower voltage means lower speed or lower maximum speed. What problem do you anticipate with lowering the voltage? Thoughts, ideas? Yeah. Hmm? Okay, so that's one challenge. Oftentimes circuits come with standard voltage requirements. So I have to interface with the outside world. I cannot change it. So I would need to have some circuits now which will sit at the boundary and which will change my internal voltage, which is controlling with software, with the outside. So that's an added complexity. I will need to have a power supply which can change the voltage. That's an additional complexity. What else? Can I keep reducing the voltage? Right, yeah, there's a threshold voltage. I cannot just keep reducing the voltage also. So there is a limit to which I can go also. Okay. And the other thing is, if these terms are dominant, okay, then what may happen is that the reduction here may be swamped by the increase here, right? So what may end up happening is that even with changing the voltage and all, I may still not balance things out, that these terms may just end up dominating over these terms. So in the presence of a lot of static power consumption, usually the strategy is race to finish, which is run as fast as possible, finish, and then shut down. Whereas in systems where static power consumption and all are not as dominant, the sweet spot may either be run as slow as possible or run at some intermediate frequency. That would dictate these things. So, by the way, complicating these pictures is a lot of these terms themselves are function of voltage, so they make things a little bit more complicated as well. Very roughly speaking, you can say frequency is, it's not, but let's say a first order model, frequency is proportional to voltage. So what you can say is this term, FV square, is nothing but F square. That's a good way of thinking about it. So power is F cube. So power is speed cube. So what that is saying is that if I increase the speed by a factor of 2, power consumption, at least this term, goes up by a factor of 8. So there's a cubic dependence. So increase in speed costs us a lot. Okay, of course, all of these other things have moderating effects on it, but so that hopefully motivates like why some of these things like shutdown and stuff like that come into play. Okay, so let's see. For some reason, my slides are not coming out right here. Okay, so technology scaling. question is, can that help us? So what happened in recent, let's say 15, 20 years is that supply voltage decreased quite a bit. Okay, so I think I mentioned last lecture that we used to be at 5 volt and nowadays it's like sub 1 volt. Okay, so supply voltage and all have certainly decreased, but it has plateaued. And the reason is, so the decrease was happening partly because of reasons of power, but partly also because of reliability reasons. If we were to keep shrinking the chip and not reduce the voltage, then the electric fields would have become very high, and that would affect reliability of the chips and all. But what has happened now is that we basically have hit the threshold, come close to the threshold voltage, and therefore things have plateaued. We cannot, so threshold voltage is blue one, it has reduced, but the gap has significantly narrowed. And as we come closer and closer, as the supply voltage comes closer and closer to this, reliability goes down. Reliability as in the chances that your volt bits will not be in the right, will not flip correctly. But the other part is leakage current goes up. The closer this is, the leakage current goes up. So essentially we have reached a stage at this stage now that voltage reduction is not there. So whatever opportunities we had, they're kind of behind us at this stage. Yeah. Go ahead.
What are the volts in the human brain? Do we know?
Good question. Anyone knows? They are in millivolts. Yeah. They are millivolts, and actually the potential across the cell membrane in a neuron is negative. Okay, so when it fires, so if you look at the sodium ion channels and the calcium channels across things, so the way their potential works. Okay, so essentially the spike which goes through, of charge which kind of goes through from one neuron to another. Okay, so you can actually mess with the brain quite a bit. Okay, so there is something called magnetic neural stimulation, but basically what they do is they place an electromagnet out here, okay, and then generate the magnetic field, which in turn interacts with the charges in there. And I was hearing a talk recently where a German group did the following experiment, where one person is thinking a bit, okay, and then they pick up through EEG the signal, they transmit it to the other person, and through the neurostimulator are affecting their state. And the idea is that can the bit be transmitted reliably? And yes, it can. The only problem with that technology is by and large safe, but it can also in some cases cause elliptical seizures. Okay, so but you can manipulate the state of the brain as well, besides kind of reading it, obviously. So anyway, that's sort of cool. Okay. Sorry. Next stuff. Okay. So what's been happening is that to compensate, threshold voltage has been lower, but as the threshold voltage is lower, besides increasing the leakage, the other part is that the speed of the circuit is decided by the gap between VCC and VT, the gap between the power supply and the threshold. So what's also happening is that you cannot lower it too much because the circuit will become too slow. Okay, so that's the other aspect which limits the technology scaling that we can do. And leakage increases exponentially as VT is lower. So leakage term out here, and then okay. So overall point out here is that good days in terms of we can keep reducing the power supply, we can keep reducing the scaling, and the scaling are kind of gone. And what has been happening as a consequence is that the ratio P leakage to P total, that is what fraction of power goes to leakage, has been going up and is actually quite high now. Okay, so it's basically roughly half the power goes to leakage, half the power goes into the dynamic or the active power. So what all of this translates into the following, that in the early days, of low power systems in all 90s and early 2000s, scaling as in reduce the frequency, reduce the voltage used to be a good strategy. What's been happening now is that this sort of run as fast as possible and finish quickly becomes intuitive, becomes a better strategy because we are dominated by the leakage part. So you want to minimize the thing. But the only way to get it to work is that you also need to have mechanisms so that you can rapidly start and shut down and start a system. Okay, so because if it takes a lot of time, lot of energy to shut the system down and restart it, then it will have consequences. And very broadly, this idea that you can scale or shut down and that you need to make the idle power consumption, the static power consumption to be very tiny, and that you need to have a very efficient mechanism to reboot a system is applicable to all types of systems, not just computers. I mean, if you reflect upon it, they essentially all our systems have similar characteristics in the sense they have a static power thing, they have something which is active. That active power tends to be monotonic with the performance. That is, more performance we need to pay for it in power. Usually, more performance we need to have a super linear dependence on power. So these are all shared characteristics, whether it be buildings or cars or computers or mobile phones. They all sort of share that basic attribute. And therefore, this general principles that I have kind of said that like at some point do as quickly as possible versus in other regimes where scaling is a good option. These are sort of shared mechanisms that you might imagine. And a couple of general principles that sort of follow from this is designing systems so that they are energy proportional, as we saw earlier in the lecture, designing systems so that they do nothing very well, namely they consume very little power when they are shut down. These are kind of desirable goals to have for any class of system, whether it's a radio or a CPU or a memory, and hopefully by making all of these together, you hit a sweet spot that your overall system can behave a certain way. So those were kind of generally applicable principles. Yeah.
How much more energy does a computer consume when it's booting up compared to when it's idle?
Good point. So firstly, it's not, you're asking a wrong question. Why is he asking a wrong question? So he asked how much more energy when it is taking up when booting up than when it is operating. So first, sorry, but okay, so what is wrong about this question?
That was my mistake, right?
Yes.
Say how much power.
How much power, not how much energy, okay? How much power, okay. So how much power is it taking up more? So now first question is, why would it take more power when booting up? What elements of a system take more power when booting up? Say it again. Well, so presumably I'm doing a lot more I/O and all, right? I mean, I'm going to be fetching a lot of stuff and all. I'm fetching the boot image from the disk and all. So I'm doing a lot more intense activity during a short period of time, whereas most other times I have all these, as I showed, like computers are idle most of the time and all, right? So the activity, the alpha factor kind of is higher, okay? So that certainly is true. What else? What are there other aspects of our system which intrinsically consume more power when starting? Nah. Hard drive. Hard drive consumes more power when starting up. Why is that? Right, it's working. So it's the static friction versus the dynamic friction. So when it's starting up, so if you look at a hard drive, it has a spike and then settles down. So now how much more kind of depends. I have a slide later on in this deck where there's some numbers for Google Glass and things like that. But the initial spike can be 2-3x, okay, easily if in terms of the sort of peak current and then going down. But there are also, even during normal operations, there are times at which these things may happen. Like for example, the disk drives are shut down, they go into sleep mode and all. So you might even see that after if you have a laptop with a hard drive as opposed to a flash drive, you would see that when you hit the button, it kind of takes the spinning up and all. And if you want to monitor the power current during that time, you'll see a big spike there. And likewise, there are spikes which happen. Like if you look at a cell phone and all, there would be spikes which are happening whenever the cellular phone is active, because that's a big power hog. So no fixed answer, but generally speaking, it is true that at the beginning there will be a spike, then it will settle down, and then there will be spikes whenever there are bursts of activities which are happening. So I'm going to stop here. The next thing that we're going to do is we're going to distill this stuff into some sort of a usable model that for power consumption of a processor that one can use, and draw some insights from that.